In this video, we are going to be getting into chapter 3, which is going to be starting logarithms. In order to talk about logarithms, we first need to start with exponential functions because what we're going to find out is that logarithms are the inverse of the exponential function. So let's go ahead and take a look at the standard form of an exponential function, which is what we're going to be using today. So standard form of an exponential is that you would have a, which is some initial value, times b to the x. So b would be your base amount. It's also called a growth factor. Your variable is going to be in the exponent for exponential functions. So a cannot be 0 because otherwise this entire thing would get canceled out. Your base amount cannot be a negative number, so b has to be bigger than 0. And it also can't equal 1 because if it was 1 and you do 1 squared, 1 cubed, all of those are 1. So this would just flatline. Okay, so a can't be 0, b has to be bigger than 0, and can't be 1. So if your growth factor or your b is between 0 and 1, okay, so like 0.5, 0.7, 2/3, then you're going to have a decaying function, okay? That means that your initial value is going down or decreasing over time. If your growth factor is bigger than 1, okay, so 1.4 or 2 or 1.03, anything bigger than 1, okay, then you're going to be having exponential growth. Your initial value is going to be going up over time. So this 1 actually represents 100%. Okay, so if your growth factor is bigger than 100%, you're going up. If it's lower than 100%, then it's going down. So let's just take a second here to analyze an exponential function, so 2 to the x. So let's actually fill in the table. I know it's already graphed, but I want to take a look at actually filling out the table just to remind you how negative exponents work. Okay, so we're going to plug -2 in, so we're going to have 2 to the -2. Remember that negative exponents mean we'll bring them to the denominator and make the exponent positive. So this is actually this 2 to the -2 is the same as 1/2 squared or 1/4. So then 2 to the -1 would be the same as 1/2 to the +1 or 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the first is 2. 2 to the second is 4, and then we've plotted those here. So the domain on an exponential function, you can plug anything into this exponent, okay? So any number can go here, positive, negative, 0, fractions, whatever. So the domain is -infinity to infinity, and you can see that on the graph that there's an arrow going to the left and an arrow going to the right and no breaks. The range, however, okay, gets stuck here at the x-axis because no matter how negative you plug in here, if you plug in 2 to the -100, okay, that's just going to be 1/2 to the +100. So it's just going to be very small, but still bigger than 0. So you have to get back numbers that are higher than 0. So we're not going to include 0, and then it can go up to infinity. Continuity. There's no breaks, like I said earlier, so then this one is continuous. Symmetry, it doesn't flip over the y-axis. It also doesn't rotate around the origin, so this one has no symmetry. It is bounded, okay? It has a lower boundary. We said it can't go below y=0, which is our lower asymptote, because this side just keeps getting closer and closer and closer to y=0. The y-intercept, so the y-intercept's on this y-axis right here. This is also where you plug in x=0. So if you're looking at the table, you'd see x=0 here. So the y-intercept is 0, 1. For an x-intercept, where does it cross the x-axis? So in a table, that would be where y=0. In this case, it can never equal y=0 because that's our asymptote. So we have no y-intercept in this case. All right, then we're going to be writing a bunch of our own exponential functions here. So let's just take a look. Let's break this down a little bit. So these two are the exact same equation, just written slightly different. So this, remember, we called the initial value. That's what this P sub 0 or P naught is. It's just the initial amount. And then what we've done is broken down the growth factor here. Okay, so this growth factor, what it is it's really 1 plus the rate. Okay, so 1 plus the rate is the growth factor. Okay, this R right here is the growth rate. So what we've done is added it or subtracted if it's going down, if it's a decrease or a decay, to 1, which represents 100%. Okay, so 1 plus the rate. Remember that your rate, when you add it or subtract it from 1, needs to be a decimal. So anytime you're using percents in with a math equation, you'd want to put them as decimals. Okay, and then T just being the time. So let's take a look at some and just analyze these a little bit for their initial value. So remember, initial value is just going to be what's multiplied by the base that has that exponent with it. So initial value here is 3. Here is 1,335, 341, 5.3. Okay, then we've got the growth factor, which is the simplified version, okay, or that whole base, right? So this whole base right here. So the growth factor is 1.2. Growth factor here is 0.9998. Here, 0.093. And here, 1.013. So that whole thing in the parentheses. Then when we go to find the rate, okay, so remember that this growth factor was 1 plus R. Okay, so we have the growth factor. We just need to subtract the initial 100% out of there. So we're going to take the growth factor minus 1 to get the growth rate. Okay, so our growth rate is 0.2. When we write this out as a rate, we'll write it as a percent. Okay, so 0.2 is 20%. And then say whether it's increasing or decreasing. So in this case, that was an increase of 20%. Okay, so an increase because this is higher than 1. So this one is decreasing because it's less than 1. Okay, and you're going to see that when you take the rate, when you take the factor, so that 0.9998, and you subtract 1, because you're going to get negative 0.002. So now when you write this as a percent, so again, multiply by 100 or move that decimal twice, you're going to have 0.2%, and then you'll say that this is a decrease. So 0.2% decrease. So 0.093 minus 1. Okay, so subtract that. And get 0.907, so negative 0.907. So as a percent, that's a 90.7%, and then decrease in this case because this was less than 1 and we got a negative. So 1.013 minus 1 here, okay, and get 0.013. As a percent, that's 1.3%, and this was positive, so it's an increase. And I'm just looking at this. This should have had another 0 in it. So this should have been 0.9998 minus 1. So this should have had 3 zeros. Sorry. Okay, so this should have been 0.0002, in which case this would be, so move the decimal twice. So this is a 0.02% decrease. Sorry about that. Missed a 0. Okay, so let's take a look. So in this one, it's a lot of words, okay, but they're giving you a formula. Okay, so they're giving you a formula right here. So using this formula, so P-E to the R-T, so you've probably seen that before. It's for compounded continuously for investments. Okay, so P is the initial amount. E is the number in your calculator, R is the rate, and T is the amount of time. So let's go back in and look. So this one says a person places $479 in an investment account. Okay, so there's your initial amount. So here's your P. Earning an annual rate. So the rate is 8.2%. Okay, but as a decimal, that's going to be 0.082. So remember, when you plug it in, you need to plug in the decimal and then compounded continuously. So if we plug those into this formula is going to be 479 e to the 0.082 t. Then this one said determine the amount of money to the nearest cent after 12 years. So we would plug 12 in for this t. So now you can just take your calculator. You can also use the Desmos calculator if you want to. So 479 times E, and if you just type in E, it'll know. And then to the 0.082, whoops. So 0.082 times 12. And then it'll give you your final answer there. And then we want to round it to the nearest cent. Okay, so this will be $1,281.39. We'll round up to that 39 cents. So that's how much is in your account now after 12 years. All right, then this next one, we have to actually write the equation here. So remember that we had that P of t equals P sub 0, or the initial amount, times 1 plus the rate, and then to the t. So an element, so this one says an element with 590 grams, okay, with a mass of 590 grams. So there's your initial amount. Okay, so here's your P sub 0, or your P naught. Decays by 19.5%. So they're giving you your rate here, remember, as a decimal. So 0.195 per minute. So they're telling you what the time is being measured in. Okay, so let's go and plug this into this function. So we have P of t equals 590 as our initial amount, and then 1 plus our rate. And our rate in this case, it's decaying. Okay, so this is going to be a negative rate, or a negative 0.195. So that it's going down, and then to the t. So our generic equation here before we start plugging anything in for time. Okay, so you do 1 minus that 0.195. So you'd have 0.805 to the t. And now this one wants to know how much of the element is remaining after 15 minutes. Okay, so we're going to want to plug 15 in here and do to the nearest tenth of a gram. Okay, so again, you can go to your Desmos calculator and you can type in 590 times 0.805 to the 15th. And it'll just calculate that for you. This one wants the nearest tenth, which is that first decimal place. So we'll round that to 22.8. So then this would actually be P of 15, because we actually plugged 15 in for the T. So P of 15 equals 22.8 grams. And make sure that you look at that, right? That this should be decreasing because it was a decay rate. So make sure that your initial amount goes down. Okay, so we only have 80% of this about left after each minute. So it's decreasing quite a bit each minute. So make sure that from your initial to your answer, it actually does go up or down, whichever one it's supposed to. Okay, then the next one, a town has a population. Okay, so we're going to have this same starting equation. So has an initial population of 10,000 and grows at 5% every year. So growth of 5%. Okay, so remember, as a decimal, 5% is 0.05. What will the population be after 5 years to the nearest whole number? So when we start plugging these in, okay, so we're going to be figuring this out after 5 years. So our t is 5. Our initial growth, or our initial amount, is 10,000. So the population was 10,000. And then 1 plus our rate was 0.05. Okay, so it's going up, so positive 0.05 per year. And then we want to know after 5 years. Okay, so you can just plug it all in like this if you would like to, just into your calculator. You can simplify this if you want to. I'll just plug it in just like that so you can see that it'll work. Okay, so you can just type in 10,000 times 1 plus 0.05, and then to the 5th, so for 5 years. So what's it going to be after 5 years? And this one wanted to the nearest whole number, so 0.8 will round up, so 12,763. So the population after 5 years will be 12,763 people. All right, this one gives you a function representing the change in quantity over t days. Okay, so the time is measured in days. What does this constant, 0.997 in here, reveal about the rate of change of the quantity? Okay, so the function is blank exponentially at the rate of what percent every how often? Okay, so decaying or growing. Okay, so this one is decaying. So this one's going to be an exponential decay. Okay, so this one is decaying because that growth factor is less than 1, right? So if this was a 1 in here, that would be 100%. So this is less than 1, so it's decreasing. And then you want to figure out the rate. So remember, you do 0.997 minus 1. Okay, so 0.997 minus 1 to get your to get this percent, so negative 0.003. Remember, that's a decimal, so you want to write it as a percent, okay, by moving the decimal over twice. Okay, so 0.3%. Okay, so this will be 0.3%. Okay, every how often. So now this one, okay, since this has to do with this, so don't just pick days, because this number up here has to equal 1 for this to happen. So this happens when the exponent is a 1. So if you say it happens in 1 day, that's actually 24 times up here. Okay, because if you plug 1 in here, 24 times 1 day, that has an exponent of 24. We need that exponent to be 1 for this to decay at that 3%. Okay, so we need for 24t to equal 1. So t is going to equal 1/24. Okay, so 1/24 of a day. Okay, so there's 24 hours in a day. So there's going to be an option in here that says every hour. Okay, so you need this exponent to be a 1 for that rate to be happening. Okay, so this one says 24t, so 1/24 would make that 1. 1/24 of a day is 1 hour. So let's take a look at this one. Okay, so same exact idea here. Okay, so this function, is this going increasing or decreasing? Okay, based on this factor right here, less than 1. Okay, so again, decreasing or decaying, whatever option they give you there. So decreasing exponentially at a rate of what? Okay, so to figure out this rate, remember you take the factor minus 1. So we're going to get negative 0.05. And then this as a percent, so move that decimal twice, is going to be 5%. So this will be a 5 in here. So 5% every how often? So take a look at this exponent. Okay, what is t measured in? So t is seconds. So we need t over 60 to equal 1. So multiply by 60. So every t equals 60, okay, seconds. So every 60 seconds, it's going to decrease by 5%. So when you can get this to equal 1. Okay, so if t is seconds, so every 60 seconds. So either there's going to be an option here that says 60 seconds, or more likely 60 seconds is 1 minute. So every minute, this is going to decrease by 5%. Okay, then this one, same idea here. So again, this one's less than 1 inside the parentheses, so this is going to be decreasing. Okay, find the rate. So we'll take that 0.91 and subtract 1 to get negative 0.09 as a percent. This is 9%. Every how often? Well, now when you look at this, this just says t. So this is already a 1 here. So in months. So every 1 month.